All right. So we are learning lesson 3.5, which it says, I may be irrational, but you're imaginary. So we're going to learn about a whole new set of numbers that you've never kind of learned. And I'm kind of excited because this is the point in, like, say, I don't know, third grade, when you used to say things like, no, you can't divide 5 divided by 2. It doesn't go into it evenly. And then you learned about fractions, and then you learned about decimals, and you're like, oh, I can divide 5 by 2, right? And so you're going to learn about a whole new set of numbers, and it's all based on this guy right here, square root of -1. And the last time we talked about how we found one of the roots, and one of the roots had a square root of -1. And that was like really weird because we talked about how you can't really take the square root of a negative number because there's nothing times itself that'll give us a -1, right? Until today, right? And so this is where our numbers, this is a whole new set of numbers. So I like saying things to my younger students of, yeah, you can't do that yet. And they're like, yeah, you mean we're going to be able to do that later on? So before, we couldn't take the square root of a negative number. And after today, you will be able to. But first, we're going to read through this. It says, relate irrational numbers to physical quantities, such as the hypotenuse of a right triangle. So if you remember your Pythagorean theorem, that's what they're talking about here. Understand expressions that contain negative numbers inside a square root, like the square root of a negative number. Add, subtract, and multiply complex numbers. Now, this is the set of numbers that we're talking about. They're called complex. And I'll explain why they're called complex in a little bit. And then, can numbers like the square root of -1 be rewritten? And the answer is yes. And what type of numbers make up this number system? Okay. So the very first thing that we're going to do is, it says irrational numbers. Verify that this 4 times the quantity of x minus 5 halves times x plus 3 halves equals to 0, and 4x squared minus 4x minus 15 are equivalent equations. Show your work and plot the solutions and the quadratic equations on the following number line. Okay, so the very first thing is they want you to prove that this and this are the same. What's the easiest way for Miss Johnson to prove that this and this are the same? What's the easiest way that I can prove that those two things are the same? What's my best friend? Who am I going to pull out? Yeah, Desmos, right? So here I go in Desmos. I'm gonna do this. And so what should I do? When I go to Desmos, what should I be doing? Yeah, what should I plug in? What should I plug in here? Yeah, I should plug in this equation and this equation. And then what should happen? What should happen when I plug those equations in? 4 parentheses, x minus 5 halves, close parentheses, open, x plus 3 halves. What should happen? Yeah, they should line up. They should be the same. Very good. So 4x squared minus 4x minus 15. They are the same. Okay, that's the fastest way for me to verify that these two are the same. Okay, let's move that out of the way. What's another way that I could prove that these two are the same? What could I do? Hint, hint on the word do. What could I do? Very good. Someone said, hey, Ms. Johnson, can we multiply these out just like you did before? Yes, we can multiply these out. So can you imagine me drawing a box and then me putting x minus 5 halves and x plus 3 halves and filling in that box? When I added these all together and then distributed this 4 all the way through, what should I get? What should I get? What should I get? Yeah, the same thing. I should get this and this. Now, I'm not going to do that because we already proved it using our graphs, but I'm just talking you through that. Then it says, plot the solutions to the quadratic equations on the following number line. Which one of these equations, this one or this one, is easier to solve for x? The first one or the second one? Which one is easier? Which one is easier to solve for x? Yeah, the first one's easier. Someone said the second one. I would disagree with you because look, this is already in factored form. So let's solve this out so that you guys are all comfortable with this. Don't choose it because it's fractions, or don't not choose it because it's fractions. Does that make sense? So I'm gonna write, let me put some lines up here so that Ms. Johnson can write straight. All right, so it says 4 parentheses x minus 5 halves, close open, x plus 3 halves equals to 0. Okay, so if this is the equation, what would be my next line in order to solve for x? If that's my equation, what would be the next thing I would do to solve for x? Yeah, exactly. I would set each one equal to 0. Very good. So I'm going to do that really quick. So I'd go 4 equals to 0, x minus 5 halves equals to 0, and x plus 3 halves equals to 0. Ms. Johnson, why did you put 4 equals to 0? Because you told me set each one equal to 0. 4, x minus 5 halves, and x plus 3 halves. But Ms. Johnson, 4 doesn't equal to 0. Oh, you're right. So we just cross that out because that's not true. 4 doesn't equal to 0. So then I would just solve the other two. So how would I solve this one for x? What would I do? How would I solve that? How would I solve that? What do I do? How do I solve this for x? Nope. No. How do you get everybody away from x? What's happening to x? Yeah, we would add 5 halves. Okay, so let me add 5 halves. So we get x is equal to 5 halves. Then I'm done. Yes? Very good. How would you solve this one? Oops, it's catching up to you. Can you guys do that for me? Can you solve this one? Very good. Very good. Yeah, you'd subtract 3 halves. Very good. X equals to negative 3 halves. Very good. So there's my solutions. Let's see. It says, and plot the solutions to the quadratic on the number line. So they're saying, oh, it's coming. So your answers are 5 halves and negative 3 halves. Where's 5 halves on here? Where's 5 halves on here? Can you guys hold on for just a second? Okay, so our job was, where do we see 5 halves on here? And where do we see negative 3 halves? Oh no, no worries. You didn't interrupt me at all. Where do we put them? Where do we put them? Where does 5 halves go? What's another way to say 5 halves? You guys know this. How do you write 5 halves? Come on. Yeah, it's 2.5. Perfect. So boom, it's right here. Where is negative 3 halves? Negative 3 halves. What's, yep, negative 1.5. Perfect, done. So they're just having you graph on a number line because eventually you're going to be graphing these complex numbers. And I want to show you that they're similar, but not exactly the same. So verify that this and this are exactly equivalent. How would you verify this? I'm actually going to multiply this out just to show you it does work. Because I think that if you see this, the more you see this, the more you'll understand how to do it. So I'm going to do that. I'm going to show you how I do it. I'm going to have you fill it in first before I get to it. So I'm going to make a gigantic box with 3 rows and 3 columns. Okay. Right. And then I'm going to fill this in. I'm going to go X, -2, and then √2. And then I'm going to go X, -2, √2. Right? Did I do that right? X, -2, √2, X, -2, okay. So what I want you to do, I know this feels weird, but I want you to multiply every single number in here. I want you to multiply every single number in here. And then we're going to check back and you're going to try to add all these things. It's kind of neat what happens. That's why I want you to do it. Okay. It's going to be a tedious task, but I want you to do it because something neat happens. Okay. I'll check back with you in a second. Okay. So we're checking in and we're going to see if we can multiply this. And again, this is one of those things that looks really complicated, but it's not actually that horrible. All right, let's do it. X times X. Very good. X squared. X times -2. Very good. This one here, I write it differently than maybe some other teachers or mathematicians. I just want to make it clear that who is inside and outside of the radicals. So X times √2, I write as X √2, because then it's very clear that X is in front, outside the radical, and √2 is, it's only √2. Does that make sense? So then, okay, so far, not bad, right? This is not bad, right? What about -2 times X? So not bad again, right? So -2 times -2, that's 4. -2 times √2 is -2 √2. Right? Is there anything horrible about this? No, right? It just looks really, really bad. So this one is going to be -x √2. -2 times, okay, so I'm going to take this one slowly. -2 times -√2. Okay, so that's going to be +2 √2. Right? And then negative times positive is a negative. √2 times √2 is, wait, so it's √4. What's the square root of 4? What's the square root of 4? Yeah, it's 2. So that's just -2. Okay, so was there anything like crazy about that? Everyone says no, Ms. Johnson, it's not that bad. So now what I want to do is I want to start simplifying this by adding like terms. So here I have X squared. So far, so good. Here's -2x minus 2x. So that's -4x. And so far, so good, because look, x squared minus 4x, right? And it's like, uh-oh, all of this is supposed to equal to 2? All right, I wonder how that's going to work out. So does anybody see anything neat that happens? Does anybody see anything neat that happens? What do you see that's neat that happens here, guys? Anybody? Come on, try. What do you notice about a -x √2? Who is his like term? Who is his like term? Yeah, this x √2. What's x √2 minus x √2, guys? What's x √2 minus x √2? One more time. What's x √2 minus x √2? I'm going to write it down. Oops. What's x √2 minus x √2? Don't make it complicated. You guys are making it way complicated right now. I could tell. Don't make it complicated. What's x √2 minus x √2? Zero. Exactly. I don't believe him. Good. Don't. Look at it. Why would this equal to 0, everybody? Thanks for taking that risk. That was huge. Yeah, they cancel out. They're the same, but opposite. A number plus its opposite is always going to be 0. So x root 2 minus x root, does everybody see that this is 0? Okay, so that goes away. Oh, that's good, Miss Johnson, because we only have 2. We have x squared minus 4x, and that needs to be 2. Okay, well, what about this? 2 root 2. Who's his like term, guys? Come on, y'all. You guys got to take risks. Come on. Who's 2 root 2's like term? Yeah, it's going to be 0 again because 2 root 2 minus 2 root 2 is going to be 0. Okay, so these go away again. Oh, and 4 minus 2. What's 4 minus 2, y'all? Oh, that's why it's 2. Do you see how we verified using multiplication? Very, very good. Very good. Very good. Okay. So with that being said, so number 1, they are equal. Okay, they are equal. And then it says graph the solutions on the number line. So which equation, I'll ask this again, which equation would you use to solve for x? First one or second one? Which equation would you use to solve for x? The first one or the second one? Yeah, the first one. Very good. Okay, so I would solve this one, and then I'm just going to write it really quick. This would equal to, and you guys can check my math later, but I want to get to the answer. It would be 2 minus root 2 and 2 plus root 2. So where do I find that on the number line? Well, first of all, you can simplify here by saying 2 minus square root of 2. Oh, that's 0.585. Okay, so you want me to graph 0.585? Sure. And then 2 plus root 2. Let's just put a plus here. Oh, and that's 3.414. Okay, that's that guy right there. There you go. Everybody okay with that? Yeah, so I've convinced you that this is the easier one to solve. I'm glad. So you may have found it difficult to locate the exact points on the number line that represented 2 solutions for the second pair, right? I just put numbers around. It wasn't exact, right? The following diagrams might help. So first of all, we want to talk about the perimeter of an isosceles triangle, right? So this isosceles triangle is 1 and 1. So can you tell me how we would find this hypotenuse right here? How would we find this hypotenuse right here? Does anybody remember? This is a right triangle. What theorem did you learn probably in 8th grade that talked about the theorem involving right triangles? Yeah, it's the Pythagorean theorem. Very good. Okay. So but the Pythagorean theorem, in case you forgot, is in a right triangle, we get leg squared plus leg squared equals to hypotenuse squared. Okay. So which one of these is the hypotenuse? Which one of these is the hypotenuse? Yeah, this longest side. It's always going to be the side that's opposite of your 90-degree angle, right? So then that is the one that I don't know. So I'm going to put x. So that's x squared. And then I'm going to plug in my 1. So 1 squared plus 1 squared equals x squared. So then you just do math. So that's 1 plus 1. That's 2. So that equals to x squared. So what is x then? What is x? If x squared equals to 2, what would x be? Okay, how do we get rid of the squared, guys? Come on. You got this. You got to interact. You got to give me some work here. Nope. How do you get rid of the squared? Nope. How do we get rid of the squared, guys? Yes, very good. We square root. Do you guys remember this? We just talked about this, right? What can't we forget, guys? Very good. Plus or minus. And in this case, we will throw out the negative because we want this to be a side of a triangle. And sides of triangles can't be negative. And I'll say the words, not yet. Okay. So we might approximate the perimeter of this triangle. So then we would add all these three sides, right? So I'm going to add 1 plus root 2. Is there anything that I can simplify here? 1 plus 1 plus root 2. Is there anything I can simplify here? Come on, y'all. I need more than one person answering or 4 people answering. Come on. Get it. Yeah, 1 plus 1, what is what? 2. 2 plus root 2. Very good. So here's our answer. We get 2 plus root 2. So we might approximate the perimeter of this triangle with a decimal number, but the exact perimeter is 2 plus root 2. So we always talk about the difference between an exact answer and approximate answer. That's important. So note that this notation represents a single number, the distance around the perimeter of the triangle, even though it's written in this sum of 2 terms. So like, think about this as like 2 plus 5. It's just a number, right? So explain how you can use this diagram to locate the 2 solutions to the quadratic of 2 plus root 2 and 2 minus root 2. Do you guys all see? Tell me what you see here. What do you see here? I need you to be great observers and tell me what you see. Yeah, you see a circle. Very good. What else do you see? You see that graph? Very good. Now, what's so special about a circle? What is so special about a circle? Yeah, pi is important. Yes, and we see that triangle again, very good. So the important thing that you need to understand about a circle is that it has a radius and a center. So it looks like the center is at 2, comma 0, and then it has a radius of root 2, right? So if this is 2, and then we have, how long is, they're asking us to find 2 plus root 2. Where's 2 plus root 2 in our whole thing here? Where's 2 plus root 2 in our whole thing? Yeah, here's the root 2. So I need you to pretend that this is a bicycle wheel. And do you see all the spokes that come out of the center right there? So those are all root 2s, right? So 2 is this 2, and root 2 is this 2. So I need you to pretend that you went on a run, okay? And you started at 0 and you went running. Good. Here's you running, you're running, and you ran 2 miles, which is great. Miss Johnson, she didn't like running. That's okay. And then you take a break, and then it says that you ran for root 2 of a mile longer, right? You ran for a root 2 of a mile longer. Does that make sense? So if I continued on the same path, where would I end if I continue running root 2? Where would I end? Yeah, which is right here at the end of the circle. Does that make sense? Good, because this distance here is this distance is another square root of 2, right? That distance is a square root of 2. So 2 plus root 2 is go 2 miles, take a break, and then continue on for root 2. Same thing goes for minus root 2. We would end at this circle. So the circle, I know, right? The circle right here is making sure that you know how long root 2 is. So this is 2 plus root 2. So this point right here is 2 plus root 2. Okay. Where would 2 minus root 2 be? Where would 2 minus root 2 be? And this was where we'll end for today. Where's 2 minus root 2? If this is 2 plus root 2, where would I find 2 minus? Yes, the left side of the circle. Very good. So this guy right here is 2 minus root 2. Why, Miss Johnson? Because you have that same distance you have another radii going to the left, and that radius is √2 long. Does that make sense? Very good. So the things that you were supposed to learn today, not a whole lot, because this is still in the intro part of the lesson, is you were supposed to remember that number one, this is an easier equation to solve. Number two, how can I verify that these two are exactly the same? Using the equation or multiplying out. And we're just getting into this type of triangle, which I will tell you right now, this triangle you will see over and over and over again in one of the chapters coming up. Okay. So thank you for listening.